Hey there, folks. I hope you had a great weekend. Thanks for tuning in. This new chapter focuses on the rotation of rigid objects. And the first one we're going to start with is a bicycle. We want to solve for the radius of the rear sprocket on this bike, given all these details. But before we start, let's take a closer look and draw a picture. Here we have the front sprocket of the bike located on the right and the rear one on the left, with this bike chain wrapped around them. Let's call the radius of the front sprocket capital R and the radius of the rear sprocket lowercase r. When we pedal forward on this bike, it will cause the front sprocket to turn with an angular velocity in this direction, which will also cause the rear sprocket to turn in the same counterclockwise manner. Since the chain is attached to these rotating sprockets, well, it has to move as well, and it will have the same linear velocity at every point in the chain. There's one more thing to consider. As these sprockets rotate, they provide an angular velocity to the tires of the bike. It's not just any angular velocity, but rather it's the same velocity that the sprocket has. So this means the front sprocket and the front tire turn at the same rate, and the same goes for the sprocket and the tire located at the rear of the bike. Let's begin by calculating the linear velocity of the chain. To do that, we're going to need a fancy new equation. This one allows us to get a linear velocity from the radius and angular velocity of a rotating object. We already know the radius and angular velocity of the front sprocket, so let's use those. And we'll go ahead and plug in the numbers for them. However, there's a problem here. The proper unit representation for angular velocity is not revolutions per second. It needs to be radians per second for us to continue. We can fix this pretty easily by multiplying this line by 2 pi radians per revolution. And this way, the revolutions units will cancel out. Let's go ahead and multiply all of this together now. Notice that we don't have radians in the numerator of the units. And that's because radians don't represent anything physical. They're a dimensionless quantity. And that's what allows us to put meters back into the numerator of a velocity where it belongs. This isn't our final answer, so I'm going to grab an extra significant figure here to be careful, and now we can move on to the next step, which is to calculate the angular velocity of the rear sprocket. This is where the hints about the rear wheel come into play. We're told that the tangential speed of a point on the rim of the rear wheel is 5 meters per second. Which is just the value of the linear velocity there. Let's divide both sides by the radius of the rear wheel, and now all we have to do is just plug in the numbers that we were given. Be very careful here and express the result in radians per second, since we've fully canceled out the meters. We'll hang on to an extra significant figure here, too. We now have everything we need to fully solve the problem, so let's go ahead and finish it up. We have the same equation as before, but this time we're going to solve for the radius of the rear sprocket, lowercase r, using the quantities that we calculated. Divide both sides by the angular speed of the rear sprocket, and then plug it all in. Since this is our final answer, let's express it using 3 significant figures this time. Here's the result. It's kind of a small number, so let's convert it to something a little more practical. and multiply this by 100 centimeters per meter. Now this looks a lot nicer, and we've matched the exact answer listed in the back of the book. That's it. Thanks for watching, everyone.